In this clip, I want to show you how we can derive the order of a reaction. And in terms of deriving, I really mean mathematically derive what is the order of a reaction. So in the first place, let's assume we have a reaction where we have a substrate, and this substrate is consumed in this reaction. And we can then write usually an ordinary rate equation. So we can write the rate equals minus K times the substrate concentration and to the power of something, let's just simply call it M. We know that K is our rate constant, and here M would be our rate order. So rate order. And you then probably ask, yeah, well, why do we want to derive the rate order mathematically? Well, sometimes the rates can be a little bit more, the rate equations can be a little bit more complicated. So, for example, we might have, for an enzyme reaction, we might have V equals Vmax times S, the substrate concentration, divided by Km plus the substrate concentration. And in this case, finding the order is not so trivial. So how can we actually do that? Well, one thing that we want to bear in mind is when we talk about order of a reaction, it tells us, the order of a reaction tells us how basically the rate changes if we change the substrate concentration. So let's write this down. So the order is basically defined as a change in the rate dV over ds, the substrate concentration. And that is what the order tells us. How will the rate change if we change the substrate concentration? Now, what we can do, obviously, we can do that for this very simple example here that we had before. So what we need to do is we need to find the derivative, so dV over ds of this equation here. And that is pretty simple. We look for the S, and from the basic rules of getting a derivative, we know that this would be minus K times M times S to the power of M minus 1. Now, this looks great, but it's in a way, this is a very specific case because we would be very specific for our K. And therefore, what mathematicians like to do is they like to normalize equations. Normalize the equation. And this is easily done by multiplying our derivative with exactly the reciprocal. So we would get for our order, we would get in the normalized form, so order norm, what we do is we take dV over ds, our substrate concentration, and multiply that with the normalizing factor, which in this case is simply S over V. And you see, it is basically the same what we have done here, but just simply the other way around. I can't say it. So let's see what we get. So for the normalized order, we then would get, well, what we just did here, minus k times m times s to the power of m minus 1. And now we add our normalizing factor times s divided by, and here we take our rate that we had up here. So that is minus k times s to the power of m. And what we see is, if we just simply combine that and make that a little bit nicer, we find that the minus and minus cancels out. K cancels out. That's great. Now we have s to the power of m minus 1 times s times m divided by s to the power of m. And if we combine that, this gives us again s to the power of m. So what we have is s to the power of m times m divided by s to the power of m. This cancels out, and our normalized order, so normalized order for this particular reaction equals m. Now, if we have, for example, the Michaelis-Menten equation, let's have a look how this would look like. We have V equals Vmax times S divided by Km plus S. So we have here the added complexity that we have basically a quotient in which our x or in which our s appears. So if we want to do dv over ds, we need to apply basically the quotient rule. And remember, if we've got something like f over g and we want to get the derivative, which I indicate with this prime here, the quotient rule basically says equals f derivative times g minus f g derivative divided by g square. So let's do that. So for dv over ds, we get, so let's get the derivative of the numerator with respect to s. So this is just simply derivative, in this case is Vmax times s to the power of 1, so this disappears, times our denominator, and that is Km plus s, minus our numerator, which is Vmax times s, times our denominator, and this basically is just s derived, which is nothing else but 1. And then, of course, we have Km plus S squared. So we can try to get this a little bit nicer. And just we multiply the Vmax in, so we get equals Vmax Km plus Vmax S minus Vmax S. Divided by Km plus S squared. So obviously this is the non-normalized form, and we see that the Vmax S cancels out here. So we have equals Vmax Km divided by Km plus S squared. And as I said, that is the non-normalized form. If we want to get the normalized form, what we do is we take our dV over ds and multiply it with S over V. So let's do that. We have just done this one here. So we have dV over ds, and we said this is Vmax Km over Km plus S squared times S divided by, and this would be, now going back to our Michaelis-Menten equation, this would be Vmax times S divided by Km plus S. So that's here this normalizing factor. So now we can start to group these things, and for the normalized order we get Vmax Km over Km plus S squared, and we can first of all we can cancel that, and then we multiply with the reverse fraction, just simple math. So we get Km plus S divided by Vmax, and we see we can cancel this, and we can cancel this for one of the squares. And for the normalized order of this Michaelis-Menten equation, we now get Km. What have we got left? We've got the Km divided by Km plus S. So that is the normalized order of a Michaelis-Menten equation. So every time you are trying to figure out the order of a reaction, and how to derive this mathematically, what you need to do is you need to calculate, or you have to find the derivative of your dv over ds and then normalize it by s, by multiplying it s times v. I hope this makes sense. Thank you very much for watching.